All right. So let's see. Our new topics are welcome. So today we are going to study some properties of operators, not wave functions. But let's see what we know about wave functions first. They are continuous, square integrable, yeah, can be differentiated two times, is quantized, eigenfunctions, normalized, etc. etc. Today we are going to see some properties of operators. So let's start with Hermicity. One thing that it always gives a real value. A Hermitian operator, we are talking about properties of operators, you see. So a operator which is Hermitian will always give you a real value. So suppose there is a Hermitian operator such as the Hamiltonian, when it will operate on a wave function such as psi, the value of the observable, that means for Hamiltonian it is energy, so the value of energy will be real. Okay, and how do you know operator is Hermitian? Okay, let's see. So a Hermitian operator will have this property. What that is? Suppose we have got two wave functions. H cap psi 1 is equals to energy 1 and psi 2. Yes, oh sorry, psi 1. And it means that it first wave function is at energy 1 and the second wave function is at energy 2. Let me just clarify this. So suppose you have got a particle and the particle is moving in some space, we don't know. So when it has energy even, its properties, its behavior is described by psi 1, but when its energy increases to, let's say, E2, the energy, the properties are described by psi 2 then. Okay, so that's what it is. Moving on. So Hermicity, that means a Hermitian operator will be such that when it will operate on these two wave functions, the eigenfunctions, in this manner, that means integration of conjugate, okay, of psi 1, let's say, and it is operating on let's say psi 2, and over some interval, let's say x1 to x2, we don't know yet, but anyway, so this, let's see what it's coming out to be. It's going to be integration of psi 1 star, and as we know, h cap psi 2 is e2 psi 2, so you will get e2 psi 2 dot dx. You can take e2 out, you will have integration of psi 1 star psi 2 dot dx. Well, similarly, if we had started with psi 2 star and we had operated on psi 1 instead, and used dx, what we will get? You will get psi 2 star, and you will get even, and psi 1 even will come out, and you will be left with psi 2 star psi 1. I forgot the dx. Okay, so these two values, they are conjugate of each other. So the two values that you will get here is, these two are going to be conjugate of each other. It means one of these, it means the conjugate of this one, let's say. Okay, so the conjugate of this one is going to be equal to this one. If this is true for an operator, then the operator is certainly Hermitian. That's the property says. And if it is Hermitian, you know what's going to happen. The value of E1 and E2 will be real values. That's it then. Let's move on to the next property that Hermitian operators often have. Always have. That is orthogonality. So you know orthogonal means perpendicular things, but no, here it means something different. Let's see what that is. Again, talking about two functions that have some values, let's say even, and let's say psi 1 again. Okay, you will again have some other property psi 2, and that's it. There you go. Let's say that it is some energy in an atom. There you have it. Okay, so when the electron moves from there to there, okay, its energy changes from E1 to E2, and the wave function changes from psi1 to psi2. Okay, in this case, the two functions are orthogonal, or you can say non-overlapping. What that means is that if you take the product of psi1 and psi2 and you integrate this value over some the tau, that means the volume, from minus infinity to positive infinity over whole thing, then you will get 0. This is a very useful property that you will see in hybridization. I mean, when we will find hybridization, you can check that video in my other what you can say, you can check that video out. Anyway, so when you find hybridization, this is a very important property, and this property is possessed by Hermitian operators again. So Hermitian operators are orthogonal. It means the wave functions are orthogonal to each other. Okay, so one important thing, orthogonally is always a property of a pair. So psi1 and psi2 are energies of the same electron, okay, and eigenfunctions of the same operator h cap. Okay, so these two values and eigen equations, that means we were considering an equation like this. But what if some function does not follow? Well, let's see. I know what you're thinking, that if a function does not follow this equation, then obviously we will not consider that function. But hear me out. So first of all, let's see that you have an equation. Suppose there is a particle. Okay, let's start with the particle. That's always better. So this particle is moving in some way. Okay, it has energy E, and you find out that the by your equation h cap psi is equals to E psi. So the energy was such that psi was actually a no, let's take it as sine kx. Okay, so the energy was such that the value of psi came out to be sine kx. Okay, now it means that the particle was moving in a sinusoidal wave like this. I mean, you can say it's not going to be imaginary in this case. So of course it is safe to consider that it is moving like this. Moving on. Now, what will be the momentum of this particle? Confused? Let's see, it's easy. How do you find momentum of a particle? Well, you operate on psi like this, and you get your momentum by performing this action, and that action is h cross by I. Differentiate its x direction, so we'll differentiate with x, right? And what is psi over here? Psi's value is given, so it is very easy. All you have to differentiate is sine kx. Well, differentiate it right now. H cross by I d by dx. Oh, you differentiate it, and what you get? Well, you will get, of course, sine kx differentiates to cos kx, and you get a constant as a multiplier. So you will get k and cos kx. You don't see anything wrong with that? Well, there is very wrong with this thing, because we were supposed to get an equation like p psi, correct? So we wanted psi back. That means finally we wanted sine kx, but we do not have a sine, we have a cos function. So what is the momentum? I mean, we do not know what the momentum is here. We are totally lost. We don't know what a momentum is right now. Now this is something like we are stuck. What should be the answer? And then we ask ourselves, no, something is wrong with sine kx. This cannot be the solution of this equation. This particle cannot move like this, and that's why we are not getting this momentum. Well, let's try that out. Let's see what can happen if psi is a solution of this equation or not. So we can check that out. Okay, h cap means minus h cross square by 2m. Okay, and differentiating a second time. but here only one direction is considered, so we will differentiate with x only. So dx square, right, plus the potential energy, which for here we are going to take v is equal to half kx square only, and as you see it will not affect the value of psi at all, so let's just not write it. Okay, so what is the value of h cap psi? Well, let's see. So minus h cross square by 2m, and the action is the second differential of sine kx plus v of x into sine kx. Okay, so what you will get? You will get a minus h cross square by 2m d by, okay, so 2 time differentiation, right? So after 1 time, what you get? You differentiate it once, you get cos kx multiplied by k. You differentiate it another time, you already have 1k, you differentiate cos kx, you will get sine kx with a minus and k one more time, so it's a square, so it is minus k square sine kx. Okay, remember, so you will get minus k square sine kx again, and as we know this is not going to affect much, so v of x and sine kx again. So what did we learn? We saw that this is going to be plus h cross square k square by 2m. I'm going to name it psi again, plus v of x and psi again. You can in fact take psi out of this equation, and what is in this bracket? Well, this is a real number, this is also a real number, so yes, it is energy and the value of psi again. So yes, this equation is compatible with psi. It means psi is indeed a solution of this equation. You get it? So psi is a solution of this equation, but it is not a solution of our this equation, that is with momentum. So in that case, what we need to do? Well, the solution, to find the solution, we take the combination of this. Let me tell you what that is. So what is basically the combination? Well, we consider that there is going to be more than one value of momentum. Yes, you heard it right. So there will be more than one value of momentum. And how do I know that? Well, there has to be some functions that will be compatible with this equation for one time differentiation. We know we are differentiating only one time and we should get the function back again, correct? So there is only one function like that, and that is e to the power x. You differentiate e to the power x one time and you get e to the power x again. So anything written in the form of this is going to be solution of this equation, that is e cap psi equal to p psi, correct? So we are going to do just that. We cannot change our original function, right? So because that's against the rules, no? That's already we have this already. So we are going to write psi in terms of c1 e to the power something something plus c2 e to the power something something. Can we do that? Yes, you can. Let's see. So we are going to use the Euler's formula, that is e to the power I theta is equals to what it is, yes, cos theta, and what it is, yes, I sine theta. Yes, you guessed it right. So e to the power, yes, you are getting it right, I x, let's say it is I kx. So you are going to get cos kx plus I sine kx. Simple enough? Yes, it is. Then e to the power minus I kx as cos kx minus I sine kx. Well, from here it is clear that if you add these two equations and then do just a little mathematics, you will get sine kx as, yes, you will first add them, kx, sorry, it's minus. Okay, so then you will get 2 ikx, and then it will be 2I, and then you will divide it by this. So divide this whole thing by 2I. Yes, that's correct. So that's how you can write sine kx in terms of ease. And let's just put it here. So instead of solving sine kx, I'm going to solve these equations, d by dx. And instead of sine kx, I'm going to write e to the power I kx by 2I minus e to the power minus I kx by 2I. And differentiating each one time, you will get, first you differentiate this 2I as it is, e to the power I kx is e to the power I kx. Then differentiation of I kx means I k, minus differentiation of this 1 by 2I as it is, and then differentiation of this is going to get you a minus ik. So it's going to be plus, and I'm going to write minus ik and e to the power minus ikx back again. Okay, now let's separate our original function. Okay, so you are going to get h cross by I. What was our original function? Yes, this is our original function. Don't forget this. This is very important. This we need to get this thing. So yes, 2I is still there and minus 2I is still there. Let me just write it in a very creative manner. This will be ik. Okay, and yes, e to the power ikx divided by 2I. Then we will have plus, and then we have minus ik. Yes, wait, I know what's happening. And then you will have minus e to the power ikx divided by 2I, bracket, and another bracket. Okay, blue bracket. There we have it. Okay, so you see what happened. This is one value and this is other value, the two functions that we initially had. Remember, we wrote psi as c1 psi1 plus c2 psi2. So psi1 and psi2 are, well, let's go back. Here it is psi, and then psi1 and psi2 are e to the power ikx and e to the power minus ikx. C1 and C2 are 1 by 2I and minus 1 by 2I. So that is e to the power minus ikx as psi2 and minus 2I as C2. So we had this already. And now we have it again. We have C2 psi2 and C1 psi1 again. Instead of, and along with that, we have two other values. And these values are, of course, the momentum values. So let's just write it on the original manner, multiplying everything. Okay, so I say I cancel, you will get h cross k, and then original value c1 psi1. Okay, plus another value that is minus k h cross, and then c2 psi2 again. Okay, so our equation becomes, let me just clear all this mess. Okay, so that's it. This is what you get. Also forget this one. So this is our equation is now. So you got p cap psi. We wrote psi as c1 psi1 plus c2 psi2. Okay, then you operated on c1 psi1 and operated on c2 psi2. Then c1 and obviously you will not get it, psi1 plus, and c2 gets out, and this is psi2. So next what you get is c1 as it is, and it was p cap psi1, and we know that psi1 is a solution of this equation, so you will get p1 psi 1. Yes, similarly you will get p2 psi 2, and this is what we have got. This is our, let me mark it, p1, and this is our p2, and the c1 psi 1 and c2 psi 2 are just right here. See, so you get two values of momentum and both are real. One is h cross k and one is minus h cross k. So we say that energy E, you have two values of momentum. So when the energy is E, you have two values of momentum that are, one is positive and the other a negative. So that's how you get a combination and a solution to this problem. So this is A now, and this is the values you get. For energy you have two momentums. One is h cross k and one is minus h cross k. So it is for like positive direction and this is for negative direction. So here you are. Now you have the values, two values of momentum. And that's reasonable. I mean, come on, the particle, why the particle will go only in one direction with this energy? If it has this much energy, then it can go in either direction now. So the particle is actually moving in positive x direction as well with a momentum of h cross k, and it is also moving in the negative x direction with the momentum minus h cross k. Sorry. Here. See, so that's how you find values of, I mean, that's what you do when you don't have the eigen equation. Okay, so that's all then. Thank you so much. Like, share and subscribe.